In this lesson, we will look at the reason autopilots were introduced, then show the typical closed-loop pilot control system, and compare it with the typical autopilot closed or inner-loop system. We will then look at the different types of autopilot, typical autopilot redundancy on modern airliners, and the EU OPS requirements. Autopilots evolved to relieve the pilot of the physical and mental effort required to fly the aeroplane manually over long periods of time. With the autopilot looking after the basic function of flying the aeroplane, it left the pilot to concentrate on other tasks, such as navigation and managing the aircraft systems. The autopilot will react more quickly to a disturbance, therefore making the aeroplane more comfortable to fly in, and allowing more accurate maintenance of heading and altitude. It takes a pilot a certain length of time to react to a disturbance, and then still further time to decide which control to move and in which direction, whereas an autopilot has corrected the disturbance in a fraction of the time taken by the pilot to react. To better understand how the autopilot controls the aeroplane, it is useful to analyze how the human pilot maintains, for example, wings level. To confirm if the aeroplane is level, you need an external reference, and this can be either looking outside at the horizon or inside at the artificial horizon or attitude indicator. As we can see, the wings are level and no input is required. In the event that a gust displaces the right wing upwards, the change in attitude will be noticed by you. By looking at your reference value, you will be able to mentally assess the rate and magnitude of the displacement. That will then allow you to mentally calculate the correction required to bring the aircraft back to wings level, and apply that correction to the controls. Having made the correction, you can see the aeroplane moving back towards wings level. When the aircraft is back to the required attitude, the control input can now be removed, and the controls set to neutral. This process can be referred to as a control loop, following a sequence of continuous events. Detection of a change from the required attitude, calculation of the correction required, applying that correction into the flying controls, checking the response of the aircraft, and removing the control input when the required correction has been achieved. This is also referred to as a closed-loop control system, as it has feedback. In this case, the feedback is aerodynamic, the aircraft letting the pilot know that it is responding to the flight control input. Now we will replace the human pilot with some components that will follow the same process that you did. Firstly, an attitude sensor or rate gyro sensitive in one axis only, that will detect any disturbance of the aircraft in roll. Attached to the rate gyro is a transducer, which is a device to convert the mechanical movement of the rate gyro into an electrical signal that can be processed. This is the rate signal. The signal is compared in the flight control computer with an attitude reference signal of known value representing wings level. When these two signals are compared, the difference between them is calculated and an error signal is produced, which is in proportion to the displacement of the aircraft away from its wings level value. With this information, the computer can then calculate and produce an electrical signal proportional to the corrective action required, a command signal. The signal is then sent to a servo motor, which converts the electrical signal into a mechanical movement to move the flight controls, again in proportion to the command signal. The control surfaces will move, and the aircraft will respond to return back to wings level. The aerodynamic feedback repositions the gyro, and when the aircraft is back to wings level, the control surfaces are moved back to a neutral position to maintain the stabilized attitude. This control loop is referred to as an inner loop. It is a closed-loop control system that will control the aircraft about its centre of gravity. In this basic form, it is only capable of enhancing the stability of the aircraft. It can also be referred to as inner loop stability or stability augmentation system. Flight guidance inputs will be looked at during the autopilot roll and pitch operation lessons. When the autopilot is switched on, it must be capable of monitoring itself for correct operation. If it fails, there must be a means to stop it controlling the aircraft. To achieve this, there is another feedback signal to let the flight control computer know what the servo motor has done. The computer is the brains of the system, and it is providing command signals to the servo motor. The feedback from the servo motor, referred to as rate and position feedback or control position feedback, is letting the computer know the mechanical movement of the servo motor. The computer can then instantly compare the movement of the servo motor with the command signal. And if there is any discrepancy, the computer will disengage the autopilot. The autopilot must not be allowed to maintain control if the servo motor is not following the correct commands. The inner loop seen here is also referred to as a servo mechanism. A servo mechanism is defined as a closed-loop control system where a small input is converted to a larger output in a strictly proportionate manner. The control column is still there, of course, but the autopilot takes control of the aircraft when it is engaged. When the autopilot is disengaged, the pilot takes control of the aeroplane manually. Closed-loop control systems having feedback are typical for this application, as the controls need to be centralized when the correction has been achieved. Open-loop systems are less common because they do not have feedback, so the control system would have no knowledge of the aircraft response to the control input. There is an inner loop for each axis of control, each having its own gyro, computer, servo motor, and control surface. Although in a modern autopilot, there may be one computer with separate channels of computation within it. Autopilots consist of either a single axis, a two-axis, or a three-axis system. A single-channel autopilot system will control the aeroplane in the roll axis only, using the ailerons. This is known as the primary axis, and at its most basic, provides lateral stability. A two-channel autopilot controls the aeroplane about the roll and pitch axes, using ailerons and elevators. The pitch axis is known as the secondary axis. A three-channel autopilot, which is standard on modern airliners, controls the aeroplane in all three axes: roll, pitch, and yaw. The yaw axis is known as the third or tertiary axis and is controlled by the rudder. The rudder channel is basically a stability channel and usually has interaction with the roll channel to assist in coordinated turns. Many multi-engine airliners have multiple three-axis autopilots to allow a measure of redundancy and to provide the ability to carry out an autoland. Each autopilot has its own three inner loops and will inevitably be powered from different generators. If the servo motors are hydraulic, they will be powered by different hydraulic systems. An operator shall not conduct single-pilot operations in IFR conditions, unless the aeroplane is equipped with an autopilot with at least altitude hold and heading mode. This means that the aircraft must have at least a 2-axis or 2-channel autopilot. During this lesson, you learned how the typical pilot controls an aeroplane and saw the components used in an autopilot in a loop to replicate the pilot's actions. You then learned about the single-channel autopilot, the 2-channel autopilot, and 3-channel autopilot. Finally, you saw the EU OPS requirements for autopilot systems.